right, guys, so I just want to give us two more practice problems we can do with potential energy. So just keeping in mind our two equations for potential energy. We have the equation for elastic potential energy. So PE is 1/2 kx squared. And for gravitational potential energy, PEG equals mgh. All right, so looking at this first problem, so we have a spring that has a force constant or a spring constant of 500 newtons per meter and a relaxed length of 10 centimeters. I want to know what is the potential energy stored in the spring when it's reached a stretched length of 14 centimeters. So in order to do this, I want you guys to try it on your own. Think about what is the value for K, the spring constant, and then remember that X represents how far the spring has been stretched or compressed from equilibrium. So go ahead and try it out. Okay, so starting out with our spring potential energy equation here, I do 1/2. My K value is 500 newtons per meter. And my X value here is 14 centimeters minus 10 centimeters, which gives us 4 centimeters. Converted into standard units, because we always convert, is 0.04 meters squared, and we find our potential energy to be 0.4 joules stored in the spring. Okay, so now we're going to do an example of gravitational potential energy. So this is something that you're going to be finding in your homework as well. So we have a child who's on a swing and they're attached to ropes that are 2 meters long. So I want to know what is the gravitational potential energy associated with the child relative to its lowest point under the following conditions. So when the ropes are horizontal, when the ropes make an angle of 30 degrees with vertical, and then at the very bottom of the arc. And we consider the bottom of the circular arc to be our 0 level, or a height of 0. All right, so go ahead and give it a try. So of course, when we're doing this, we always want to draw a picture. So at the very top, here's the child partway down, and here's the child at the bottom. So at the very top here, the potential energy is just going to be based on the height of 2 meters above the ground. So we know that the length of this rope is 2 meters, so that's the height of the child above the ground. So at its top position, PEG is going to be 40 kilograms times 9.8 meters per second squared times, running out of space, 2 meters. So we find the gravitational potential energy to be 784 joules. Okay, so now at this point right here, this one's going to be the most difficult one. I want to find out what is its height above the ground. So this is going to require a little bit of trig. So we know it makes a 30-degree angle with respect to the horizontal, and I also know that this entire length is 2 meters. So I want to know what is the length of just this part of this right triangle that I've created. I'm calling it X right now. So I have the adjacent side, and I know that the length of the rope is the 2 meters. So I can say that cosine of 30 degrees is going to be adjacent X over the hypotenuse, 2 meters. So 2 meters times cosine of 30 degrees will give us this little piece of the triangle here. But I'm interested in the height above the ground. So in order to find that, I want to take the entire length, 2 meters, minus this little portion that I found X. So the height above the ground is going to be 2 meters minus 2 cosine of 30 degrees. And I find the height to be 0.27 meters above the ground. So now to find the potential energy, PEG, I just do mass times gravity times height again. So 40 times 9.8 meters per second squared times 0.27 meters. And I find her potential energy at this point to be 105.84 joules. Okay, the lowest point is going to be pretty easy because she has a height of 0, so putting that into our MGH